So imagine we have two particles, each made of different material, and they're separated by a solvent. So for this we need the Hamaker constant H123, where 1 and 3 are the two materials and 2 is the solvent. So let's draw a picture. So in this diagram we've got nanoparticle 1, nanoparticle 3, and then particle-sized globs of solvent. So these aren't actual particles. These are just imaginary. These are just packets of solvent. Okay, so we can see if we were to bring particles 1 and 3 together, we're going to gain a 1-3 interaction, and it's easy to see that we're going to lose a 1-2 interaction and a 2-3 interaction. What's not quite easy to see is that when we squeeze this solvent particle out, it's going to interact with more solvent. So we're gaining a solvent-solvent interaction as well. So let's summarize that information. So we can say that H123 is equal to that we're going to gain an interaction between 1 and 3. We're going to gain an interaction between two solvent globs, but we're going to lose an interaction between solvent and 1 and between solvent and particle 3. All right, so we can take this, we can use the geometric mean approximation here and here and do a few steps. And when you're done, we get that H123 is approximately equal to this product, where we have H11 minus the solvent H22, and we have H33 minus the solvent as well. And if we look at this, we can see there's no reason why this number has to be positive. It could be negative, which means that it could be actually repulsive instead of attractive. So this is the first time we've seen repulsive interactions for Hamaker, and it's not really that necessarily, it's not that 1 and 3 are repelling each other, it's that the solvent is that the net effect of all the interactions pushes them apart. So it could be the solvent, for instance, is that wouldn't work. It's not that the particles actually repel each other, it's that they're interacting with the solvent, and if their interactions with the solvent are stronger than the interactions with each other, they're going to tend to be separated by solvent. So they're going to stay dispersed and not be attracted to one another. So let's see what this looks like. So when will this be negative? We can see that H123 will be negative, in other words, a repulsive interaction, if there's one of two conditions. If H22, the solvent's Hamaker constant, is less than H33 but greater than H11, or if the reverse is true. So simply put, if the Hamaker constant of the solvent is intermediate between the Hamaker constants of material 1 or material 3, if it's intermediate between those two values, then this is going to end up being a negative number. And so this leads to repulsion between 1 and 3. So in this example, we've got a little air bubble and a sapphire bead, and they're separated by water, and we want to know if they're attracted or if they're repelled from one another. And we can see, if we plug in the Hamaker constants for these numbers, for these materials, that air, it's approximately 0, water is 3.7, and sapphire is 15.6. So we expect that, yes, indeed, there will be a repulsion between the air and the sapphire because the water's Hamaker constant is intermediate between them. And if we were to come up with an estimate for H123, we have each Hamaker constant minus the solvent's Hamaker constant, and we can see this comes to minus 3.9 times 10 negative 20 joules. So negative Hamaker constant always equates to a repulsion. By the way, the experimental value for that is actually equal to negative 3.78. So it's actually a pretty good estimate.